somebody confirm from your end?
Yes, sir, we can hear you.
All right, it seems to be fine. Shall we start with the introductions we missed on the last day due to my mic and speaker settings? Would it be possible to, or probably you can start, Takura. You can start the introduction from your end, then I can move to others. Please introduce yourself.
Yeah. Good morning, sir. I'm Takura Ramakrama.
Okay.
Currently working at Civilization Authority as a manager ICT.
Excellent. Okay, this will be useful then in terms of all of your troubleshooting and the planning as well. I think we are mostly covering these things like the strategies and all the academic stuff initially. Then thereafter, you'll be going the practical aspects based on the theories what we are learning here. So probably this will be useful in terms of the management plus kind of a knowledge you require for the planning CIO, I guess. Okay,
Yes,
that's
sir. Definitely, it will be help.
all right. Thank you. Let's go for the next one. Tanushka, are you there? Okay, let's go to the another one. Tanushka, if you can unmute, then you can start the introduction. Otherwise, I'll go for the next one. Then there is another one again. Harshpriya, if you can unmute and introduce yourself. Harshpriya Rajakaruna.
Yes, sir.
Yeah, can you introduce yourself, please? Because we are on the introduction sessions which we missed on the last day.
Okay. I'm currently working as a teacher, and earlier I have worked as a network manager, assistant network manager at Rajarata University of Sri Lanka.
Okay.
Okay. Now I'm not in a job actually.
No problems. Are you do you have any past experience on network troubleshooting and the deep dives?
Yes, I have some experience.
All right, that's fine. Then mostly, as I initially explained, we'll be going through the theories initially based on the troubleshooting fundamentals. Then we are going deep dive in terms of practical applications as well as the modern day network troubleshooting. So this will be useful then. All right, thank you. All right, let's go to the another one. Let's Dinuka Rajaguru.
Good morning, sir.
Ah,
I'm Deepika Rajaguru. I'm working at Ministry of Health as an Assistant Director ICT.
all right, excellent. Are you getting involved in the networks or planning or kind of a planning for the troubleshooting or the management sessions?
Yes, sir. Yes, sir.
All right.
Overall.
Okay, that's fine then. If you have any questions in terms of network design or architecture or the planning of the network continuous monitoring or the life cycle, probably you can ask anytime. So thank you.
Yeah.
Right. Lakshi Kumanayaka.
Yes, I'm Lakshi Kumar Nayaka. I'm working at Bank of Ceylon as IT security engineer at IT security unit, and also I'm working at security operations center as well.
Excellent. Are you more towards on specialization of security or you're more of IT management?
Security, more about security.
All right, excellent. So there are sections which we'll be covering in terms of the multicast and other various traffic types of security. So probably the latter part may more impress in terms of the modern day network security implementations, plus the new workloads like which we are covering in terms of AI and ultra low latency systems, especially targeting the banks and financial institutions as well. All right, thank you very much.
Okay, so thank you.
Okay, let's go to Danushka Udayanga. Danushka, you there? Probably you can unmute. Okay, let's check with Tarindu Vijay Singh. Good morning. Okay. All right. What about your thoughts on the last week? I was explaining the view of application view, which is usually the software engineers and architects sees the world without much of a deep dive in terms of network. Do you agree with that, or you have some other views? Okay. All right. All right, excellent. Because when you are developing something, probably you need to get in terms of deep dive of the systems rather than just applications sometimes, I guess. Because when you are growing with the career ladders, probably you need to work as software architect or system architect. Probably that's the knowledge you are gaining with these courses may be really helpful, I guess. All right, thank you very much for the introduction. Okay. Let me check on Chamika Veerasinghe. If you can unmute. All right.
Good morning, sir. I'm
Good morning.
Chamki Veer Singh. I'm working in Exchange Group Private Limited, working
All
as
right.
a Chief Technical Officer.
Okay, you are the CTO there, right?
Yeah.
Okay. Probably, so that's why we are covering the initial sessions based on the fundamentals as well as the life cycle of the systems. So most probably the initial parts mainly covering the knowledge of CX, CTO or CIO level of knowledge which you require to plan on your network troubleshooting, and especially the course. The last week we have been discussing network risk management. Today we are on the network complexity and the failure scenarios. Probably this may help you, I guess.
Yeah.
All right. Thank you
Thank
very much. All right. Let's get the introduction from Mangalan. Mangalan, would you mind unmuting and
Sir, I
introducing?
think Mangal is while joined while traveling, and his message to this soon.
Ah, right. Okay. No problems. All right. That's okay. Let's get the introduction on another day. And we got somebody named Mario Prasanna. Would you mind?
Good morning, sir.
Good morning.
I'm working at Sri Lanka Telecom as a project engineer. Currently, I'm working under Fiber Projects Division.
Excellent. So this really matters directly to you. What are the areas we're working on? The fiber to home
Yes.
or any other?
No, enterprise fiber. Basically, I'm working with enterprise fiber for the enterprise, wholesale, and the government sections. The direct fiber we are managing. And previously, I worked with VPN divisions as well.
Ah, excellent. So you have the understanding of physical world and the knowledge of VPN as well. All right, excellent.
Yes, sir.
So you can share your knowledge if you have any concerns or if you have anything to add on our discussion, please proceed with this. The learning from peers will be really interesting in terms of master's degrees, because it's not like undergraduate degree programs. You can learn from peers which heavily involved in the industrial expertise and the projects related to that. That's really helpful. Thanks for being with us. All right.
Thank you.
Thank you. Anybody else I missed in the introductions? Please introduce yourself. Okay, probably we can start. So you may ask questions at any time, unmute and ask questions anytime, or raise your hand by using Zoom app. Or you can just type the questions on the chat. I can address and answer. And additionally, I will be sharing my my email address. Probably you can send emails. This is the email address I am most of the time I'm reading at least once per day. So this will be helpful for you to get in touch with us. So let me start the third session. We have already completed a couple of sessions. The first session on the 8:30 to 10:30 on the last day, and then we had a break. Thereafter, we had another 2 hours. So the similar arrangement will be followed on today as well. So let's start on the session 3 with a small recap in terms of what we have learned on the last week. Last week we had introductions in terms of the course and as well as the coverage and the definition. And I have been starting from the zero, which is defining the parts of the network. We discussed on the common application view, then went into the network boundaries, and I explained we'll be extending the boundaries beyond the switch ports, and the host-based networking will be covered in this particular course, which is the end-to-end networking. And I have been explaining you the modern secure network architecture stuff and the life cycle. This was the slide I was explaining in terms of generalist view and the expertise view, and I wanted to just convince you why we are learning in terms of this network engineering stuff within the Masters of Cybersecurity course. So it is some kind of a improvement which we can define as jack of all trades and master of. You are mastering with the security stuff, but you need to scale, bring up other associated areas as well. Then you are getting the full view of the entire business process and the IT system and how it matter in terms of your specialization. Plus, when you're designing a large system with applications, you may need full view of understanding with your certain area of specialization. So that's the idea behind this. And we were defining the parts of the network. We discussed on the application hosting and by using two hosts and interconnected by using network devices and cables with a simple view. Then I put up an idea of something like common application view. The application developers usually see something called sockets, and they're writing applications to socket, and the system engineers and network engineers take it from there onwards. So they're not very much worried. They don't need to worry in terms of complexity of the network based on their functionality assigned. It's a kind of an idea of alienization of work, because you don't need to worry on somebody else's worry on the entire system, but there are specialists on those areas, but still there are advantages and disadvantages. So when you are dealing with the different the application developers, you may need to understand their way of proceeding their work based on their perspectives. So basically, they are not very much worried in terms of how network or the systems running. But there are systems which require the deep knowledge in terms of hardware and the infrastructure stuff. That's called low-level development. There are several abstractions in terms of when you are developing large application or the serious mission critical applications. Sometimes there are application developers which are developing the application on top of middleware taken care by different types of developers which are mostly related and knowing the hardware stuff as well. So it is kind of a view you can get understanding in terms of application development, because the ultimate goal of the network is running the application smoothly by using the network and the entire system. And this is the definition what we are planning to cover in terms of this particular course. We are not limiting the course to network devices and cables, but we are working on the host-based networking stuff, including the kernel-based or operating system-based networking and other drivers and all those stuffs on the servers as well as the clients. And usually the network division in terms of modern day practice, it's divided among system engineers and the network engineers. Network engineers usually take care of network equipments and the cables between that. They are not very much keen on the host, which is with the operating system than the servers. But in terms of modern networking, especially on the virtualization, VMware, and again, in terms of cloud, this demarcation is no longer valid, but mostly in terms of on-prem systems, this is still the practice. It may change, I guess, in terms of different disciplines like DevOps or network ops or the system ops all getting integrated sometimes. And this was the idea I initially mentioned you, that the enterprise campus is a kind of a set of buildings located in a single area. I mentioned that the campus is not something equivalent to university, but its definition comes under the bunch of buildings situated on the same land area. For an example, University of Colombo, we call that as Colombo campus, but there can be many other campuses. For an example, previously there was something called University of Ceylon, I guess. After initiating the first university in Sri Lanka by British, they established two campuses. One is Colombo campus, other one is Kandy campus, which is now Peradeniya University. The university can have multiple campuses, but usually the idea comes defined as the campus is number of buildings located in same geographical, same land area. So when you I put up an example design to interconnect these different buildings. I initially mentioned on this particular slide, and then thereafter we need to learn by this at the end of this particular course. We need to have fair understanding why we connected this equipment in this particular way. For an example, we were discussing the ideas of redundancy, why that's something, that's the reason we are having a couple of switches on the distribution layer and the core layer. And there are different layerings, which is there are core layer switches, distribution layer switches, access layer switches. So we will be going into the deep dives of understanding of different layering of the networks and the purpose of layering and the maintaining the redundancy and the resilient improvement of the resiliency. All the aspects will be covering, and you will be getting understanding of this particular design, why we are having different layers, why it's connected this way, and we have a bunch of fundamentals when you are designing a network. And then we have similarly on top of that, we can define how we are managing, how we are troubleshooting when there are issues, how we are continuously monitoring and improving. All those can be a part of this lecture series, and we'll be covering most of this. And at the end of the this particular course, you need to get this the building layout, which is the zero without the network, and you need to become a hero of getting understanding of this, all the interactions between different building, how interconnected, how each component used in a different environments, or why we need to connect by uh, with the redundancy. All these ideas we'll be discussing within this course of the all 15 sessions. And we had life cycle defined here. More some of the students here are from the IT management management layers or the carriers. Probably these network life cycle lessons are pretty much important in terms of management of network, or not seeing the network as a one-time deployment and get rid of it. Usually the network should be managed, and investment should be secured for a certain period of time until your ROI covered up. And if there are requirements to scale the network, then you need to get understanding of how to do it by using continuous monitoring and improvements. So that's the idea behind the life cycle, which we have discussed. The PPDI00 is one of the famous methods introduced by a company called Cisco, or network vendor called Cisco. They were the largest vendor until last month, I guess. Yesterday I have seen a article that now NVIDIA networking has taken the position. Now previously Cisco was doing 8 billion or something like that. The NVIDIA networking has taken over with their huge data center networking sales, I guess. So probably most of these the theoretical or fundamentals emerge with the vendors, and then they become norms of the industries, and some of them ratified or defined as industrial best practices and the standards as well. So this PPDI00 life cycle approach is quite common among the industry. And there can be multiple approaches which you don't need to copy all the most common ones. You can customize your own life cycle approach. There can be something like this: the plan, design, implement, operate, and optimize. Then there can be a retire stage as well after a certain period of time. For an example, you have been using your network system for 5 years, and you need to upgrade it to support latest based on the business growth after 5 years. Then you can consider initially just for upgrading within the same frame of architecture which you have defined 5 years back. Maybe it's not valid after 5 years because you need to run the new applications such as ultra low latency and the kind of AI workloads which may not suitable for modern day applications. Then you can consider retiring rather than investing further on the same architecture which you built or expanded. Then you can introduce retire pace and then restart with a new approach or same life cycle approach. And I have been discussing the details of each phase and what we are doing in terms of there. And finally wanted to give you the perspective of multidimensional relationship of the life cycle of each stage, because it's not only clockwise movement from step to step. There can be feedback loops as well. You can come back to if you have found any issues on later stages, you can come back on the previous stages and discuss with the stakeholders there. For an example, if you find out an issue at the implementation stage, you can go back to the design stage, which design engineers or design architects, and discuss your issues and maybe revise the design again. And if designers have issues based on the planning stuff they received to design the network, they can clarify the things with the planning team and get the understanding, something like budget constraints or the business requirements. You can clarify at the going back to the planning stage. So this is again, you need to keep in mind, it's not just one way clockwise process. You can go back to the feedback loops and corrected within the life cycle. So I have been sharing a few reference book if you need to go ahead on in terms of deep dive. And I additionally, for your course officially, I think computer networking, a top-down approach, the 7th edition is fair enough, but if you want to go into the latest stuff, you can consider getting this computer networking top-down approach 9th edition. I think there will be new books in your library as well on 9th edition. Still haven't clarified, but I informed your coordinators to get few books and few books for the library with the 9th edition. Okay, that's about the first session we had. And again, in terms of second session, on the last day, we have been discussing the troubleshooting approaches and started troubleshooting fundamentals, since we had little time, the spare time of 30 to 40 minutes, I guess. We have been covering fundamentals of network risk management. Now today we can start on the complexity stuff. Network troubleshooting approaches, we discuss 6 approaches. Initially the top-down approach, bottom-up approach. Top-down is we are starting from the application layer to the bottom, and the bottom-up I have given you an example for each approach, which can be useful in your final examinations as well, in things like scenario-based questions. The bottom-up approach, it starts from the bottom layer of the OSI model, which is the physical layer. You can start the troubleshooting from the cabling and all those stuff. And then there is something called divide and conquer, which means if you have a gut feeling, you don't need to start from the top. You don't need to start from the bottom either. You can start from the middle, like from the middle layer, something like transport layer. If you have the result of testing application like ping, probably you can start from there based on the results and go up or down considering the outcomes you are getting with the test tools. And there's the fourth one is follow the path troubleshooting. We'll be discussing details on today, something like using the traceroute tool. I was explaining that ICMP is the protocol we have been using from the TCP stack for the troubleshooting. This is just sending ICMP echo request and receiving a echo exceed messages. And I introduced the concept called TTL, time to live. When you are sending a message by using the by using the tool of this trace route. You are sending ICMP echo request with the time to live equivalent to 1, which means the first layer 3 device, it will return back. Then the TTL usually represent the layer 3 hops. It doesn't expire on the layer 2 hops like switches. Usually on the layer 3 switch interfaces or the route interfaces will be expiring this TTL time to live parameter and return back with the echo proceed. This particular trace route application is doing the first packet, it will be sending with the TTL1. Then once you get the acknowledgement or ICMP echo message as a return, then it will be sending the next packet with the TTL2. Likewise, it can be monitored the entire path from source to the destination by increasing the TTL value increment by the each step. So until you reach the destination. For an example, in this diagram, it's showing two routers in between, and source is sending the message initially with the TTL1 and first router responding, and the second packet is with the TTL1, TTL equivalent to 2. Then it's returning back with this from the second router. Then finally it's sending a message with the TTL3, and it's receiving the message return from the destination server or the destination host. So with the output of trace route, you can see the number of hops from the source to destination. If any of intermediary devices failed or to respond, then there can be two reasons. One is ICMP has disabled, and other one is other one is the device is defective. So we can discuss details on today as well. Okay, that's about follow the path troubleshooting approach, and we discussed on the compare configuration troubleshooting as well. If you are in this particular case, if there is a working device and if there is a non-working device, or if there is issue on the second device, then you can compare the configurations to quick resolutions, because if you start the troubleshooting process, it may take time with a standard approach. But if you need to resolve it quickly, probably if you have two devices with the equivalent almost equivalent configuration, you can just verify, compare working configuration with the non-working or the configuration device with the configurations are having issues, or the device is giving you troubles. So then you just need to match the working configuration and non-working configuration and correct the configuration if there is a mismatch against the working one. So this is the idea. Sometimes it is quite useful, especially if you have in this particular exam there are a bunch of couple of branch routers, branch 1 and branch 2, and your head office router is working fine with the branch 1, but your branch 2 is not connecting. Then you just have to compare the branch 1 and branch 2 router configurations and compare the configurations if there are anomalies, and correct them. Other than troubleshooting from end to end, it may take time, but this is quite a fast approach mostly network engineers are doing in terms of their day-to-day work. And then the last one, which is the sixth one, swap components troubleshooting approach. This is a kind of approach. Again, if you don't have access to the configurations or the details, for an example, you're a system administrator or network administrator, you are in a small business environment, your system or network administrator on leave, and you need to find a solution to work with your colleagues. So in this case, for an example, the one of your common application is not running on the machine B, and it's running on all other machines. So you can just swap your the laptop B to another port, which is on the A, just removing it temporarily. Then if it is working on that port, then definitely there is a network issue and not your application on the laptop B. Okay, it's a kind of just swapping the components, sometimes make it resolve or troubleshoot fast. So those are the 6 common troubleshooting approaches we discussed. There are more, but for the limitation of the time constraint, we have only discussed these 6 troubleshooting approaches, and this will be tested on your assignments as well as it may test on the final examinations as well. And we discussed on the definitions, and mostly I wanted to give you an impression that network is mostly a virtual space rather than bunch of hardware equipments or routers which are tangible, because this control plane or data plane stuff we are discussing is more important rather than just thinking in terms of understanding it's something related to hardware, but most of the issues which will be which usually handled by network engineers are mainly on the control plane stuff which we are working on now, configuring or troubleshooting. So just take an idea, network is mainly a virtual space, not something which is just hardware or something like that. And we'll be discussing network functional virtualization as well. So in there, we are discussing further on this aspect. And we had some the simple maths to calculate on this uptime percentage per year. It's usually taken with the expected uptime, which is in this example, we have been discussing that 1 hour downtime, which is per entire year, you have 365 days and 24 hours per day. And just reduce 1 hour from that and divide by total hours and make it percentage. That's the usual way of getting your uptime based on your business expectations or uptime expectation. There may be situations in modern day, usually almost all the applications run on 24/7, but there are special situations like some of the banks usually work from 9 to 3. So there are situations 5/8 or something like that applicable. Based on your number of total business hours, you can calculate expectation of uptime, which is sometimes the organizations make a notice on their downtime, mentioning this application will be down for this period of time. So you can plan your downtime, so the maintenance or unexpected troubleshooting or unexpected issues, you can plan ahead with this uptime calculations based on your past experience and the projections you are getting. Right, I highlighted, then we started on the risk management aspects based on the number of devices increased in your network based on the scalability requirement. It will then you need to consider on in terms of increase of failure occurrences. Because number of devices getting increased, then definitely it will increase automatically the number of device failures as well, because more devices, more failure occurrences. So you need to consider enhancing your support team or the network ops team, which is to attend those, or you need to consider in terms of design methods, scaling, how to avoid these occurrences or reduce these occurrences with the scaling. Scaling is not something linear, but probably you can get an idea in terms of just an idea. While increasing number of network devices, it automatically increases the failure occurrences, which may impact your entire network failure or partial failures. Failure. And again, I wanted to establish the idea in terms of the bell curves. Usually people see everywhere the bell curves following, but for the networks, it's not the case. Networks usually have the different curves when you're evaluating, so you can't use the mean and standard deviation and all those aspects sometimes when you are planning your network based on the different curves. So you need to get understanding of what's the curve you are following. You need to follow in terms of predictions, and then use those statistical methods to predict the scenarios. So it's just don't stick to the normal distribution, which is the bell curve. So that's something important in terms of network risk management. And then we discuss three types of exposures, which are given the idea of fragileness, robustness, and anti-fragility. This anti-fragility is a bit of new idea, which is evolving in terms of this machine learning and AI stuff. Previously, we have been defining the network to establish on the robustness against the fragileness. Fragileness is if you design a network without a care or without following the design fundamentals, then it's kind of equivalent to house of cards, which is always fragile. But you need to the traditional network target was to build network to against the to implement the fragile robustness, which you are coming back to the previous stage. If there are failures, can be automatic, or it may be a workaround which you have identified before. If something happens, you know, you address it to handle automatically or by involving the support team within acceptable time. So recovering back to the previous working stage is the robustness, but it's not opposite of fragileness, because it's maintaining the status quo, but or the same state of working state of the network. But the modern network designers are thinking the ways of using AI and ML for the anti-fragility, which is the clear demarcation of fragileness and the opposite of it, which means if there is an issue or the impact to the network, then it will learn something from the impact, and it will improve further with other possible scenarios in future as well. That's a kind of prediction and learning from the mistakes. So learning from the failures and improving your systems for many other scenarios, including the what's happened there. So it's a kind of evolving networking, and I have given examples of house of cards for the fragileness and other domain examples. Then I mentioned that Phoenix, there is a mythical Greek mythical bird. It's named as Phoenix, and if something that's the equivalent of robustness, if Phoenix dies, then it will reborn again, reborn with the same characteristics. So there is virtually you can't kill it. So that's the idea of robustness. But anti-fragility, it's somewhat similar to another Greek mythical animal or creature. It's named as Hydra. The Hydra is a large snake with multiple heads. If you chop or if you cut one of the heads, then you get two heads from that place. So you can't kill that. If you try to harm it, then it'll improve further with getting more heads. So that's the idea behind the anti-fragility. Okay, then we had something called this impact of risk and the probability of occurrence with a quadrant discuss. And we discussed details in terms of black swan events, which is having the high impact but very rare. I taken another domain example, which is something similar to the tsunami. We haven't seen a tsunami for many thousands of years. Most of us never heard of it, heard the name. Suddenly, it made a disaster with a huge impact to the country, and we lost several lives there. Now we know what it is. There is something called tsunami. This can happen, and we have the idea. But it's a rare event, but impact is very high. So network may have those impacts, and those are the ones we need to care in terms of more, because the known things we can address and take measures in terms of corrections or the workarounds. But if we need to expect something in terms of catastrophic, may your network down entirely, but there are ways to handle that in terms of risk management. Even if you don't know don't experience the issue, the first this anti-fragility approach can be taken care of with the modern networking infrastructure to handle these kind of stuff. But there are other ways as well to handle. Okay, I have begun giving. I have added a bunch of reference book on the black zone. There is a book risk management book written by somebody named Nassim Nicholas Taleb, who is a famous trader and one of the philosophers. He have been this book basically people call this as a prediction to 2008 financial collapse within the world, and it's a kind of the good book to follow if you're interested in further risk management stuff. And we'll be learning a lot some network complexity stuff today, and I have included a couple of books there, and these are the reference books. Okay, I just wanted to go ahead with the recap, taken more time because the lessons we are learning today is quite connected to those. Okay, let me go into the network complexity after the so the green I marked by green color on the areas which we covered on the last week, and we'll be planning to cover the red sections on today: the network complexity and network failure scenarios. Basically, we are covering now on the network troubleshooting fundamentals, and we covered the risk management, and today covering the network complexity. And then the network failures by separating it to control plane, data plane, and management plane. We need to get understanding all three planes in terms of network failures. Then we will be discussing briefly about the software and hardware failure differentiation. On the next week, probably we can, on the next session, the second session on today from 10:45 to 12:45, we can proceed with the performance degradation and failures with the performance metrics. And next week, it is on after the April New Year, I guess. On 18th, we can start on scaling, aggregation, resiliency, and redundancy, and failure modeling. I think I can give you an assignment today based on our coverage for the first 4 sessions. So you have enough time to submit it. I can give you 2 more weeks after 18th as well. Let me upload on the next week, and probably you have enough time to submit it based on the first 4 lessons or lectures. Then let me check the possibility of having few more instructor-led troubleshooting sessions. Let me check with the course coordinator and arrange it. if it is possible, because they have several issues in terms of this government regulation on the government instructions on minimizing the fuel usage and all those things. Let me come back to you on this, how many sessions we can plan and when we can plan for the practical sessions. But while I'm doing lectures, I will be covering some of the practical aspects without waiting until these things, what the practical sessions scheduled. Okay, before we go for the session 3, any questions? Probably can raise your hand and type the questions, or just unmute and ask the question. Okay, let's start with the complexity. So we have been discussing the risk management stuff. Now about the complexity. So first, let's define the idea on this as well. Computer networks are complex. That's a phenomenon or the one of the beliefs. So let's go into the details of that. But what does complex computer networks are complex means? Let's understand what is complexity first before we discuss the network complexity. Complexity is anything which on layman terms I don't understand, and complexity is anything lot of dynamics, lots of dynamic parts, which means if you have something unknown to you, at least, then it is complex to you. It is subject to your perspective. It is complex. So the previously we were discussing on the developer perspective. For developers, they have understanding of all the complexity on the design application design patterns and all those network, the software frameworks and the tools there, the programming languages. That's they have the knowledge of all the complexities there in terms of application development, but they may not have deep understanding on the networks or the systems the applications are running on. It is somebody else's expertise. So basically, the networks is more complex to them, considering they don't they don't have deep understanding on the networks, but they have their specialization on the application development. So complexity has the view of not having the understanding of a particular system or particular operational procedure. That's one of the aspects. Another aspect is if you have lots of dynamic parts, not the static parts. If you have a dynamic system or progressing system with having lot of dynamic parts with the interactions or dynamic components with the interactions, then it is also considered as complex, something complex. All right, those are the two major aspects in terms of layman terms for the complexity. So let's move beyond of this particular, the two points of understanding. Moving beyond these, it's important to consider complexity as state versus intent. And then finally, complexity with the law of unintended consequences. The state versus intent underlined here. So you may maybe your network designers design the network with a purpose or based on the requirement they have received on the planning phase, which is the life cycle, based on the business requirement. They intended design the network with the intention to get the output, application output, or doing something related to the business. But even they predicted with the network design, if it is operating against the intent or the purpose of design, then it is something else, because you are getting something unexpected, which is not addressed in your design phase to tackle, or quite unintended, then it is about state first intent. So if there is a mismatch between expected state and the intent, then definitely there is a complexity, because you design the system with predicting or expecting something, the function as a one way, but it providing different unintended outputs. So that's something complexity, because there is a gap between your real system and your design. And then if there can be complexity with the unintended consequences. We have been discussing previously these black swan events. So these are rare events which we haven't heard sometimes before, and it's making high impact to your business or the applications. So it can be something you can't. It is difficult to, because you don't have prior understanding, and you are getting hit by these unintended consequences. Or again, it's almost same thing, but the idea is, if you don't have understanding of something and a lot of dynamic parts, and again, in terms of there is a gap between expected design and the outcome. And if you have unintended consequences or outcomes, which you can consider as second order effect, because for an example, now there is a war in Middle East, but there is no war in South Asia. But we are affected by the war there in Middle East. But usually the first order effect, which is the Middle Eastern people impacted there, but as the second order impact due to the fuel shortage, which is coming from the Middle East, we are affected even we don't have a war. So, similarly, in this case, you define a network or design a network. Now it's running, and running, even though it's running, but without following the intent, which means you are getting unintended outcomes. Then again, there can be second order effect due to that initial impact. Then there can be more impact, cascading impact to your entire network or the applications. So that's what we want to define as complexity. So if something is not working as per the predictions, then you are getting complexity. That's the simple idea behind this. Any questions, or if there is anything to add from your end, probably you can raise your hand or add your views. Okay, this let me take another example to explain the idea behind. So let's compare the cat first washing machine. The washing machine is quite predictable by its operation, because if let's say you need to wash some clothes, you just put them into the washing machine, and you just need to press whatever the buttons there, and thereafter you are getting prediction that it will be done within 20 minutes. So it's quite predictable. So it's your clothes will be washed, and you can get it back after 20 minutes. It's quite predictable by its function. You don't need to worry after 20, you just have to come back after 20 minutes. It's there with the washed clothes. But the washing machine circuitry, yes, it's can be complicated for you, because you are not electronic engineer, and if you are not an electronic engineer, the circuitry can be complicated, but it's not complex by its function. circuitry or it's built or it's the production can be complicated, but its function is not complicated because it's quite predictable. So it's not something complex by its operation. So at least, so there is a clear difference between complicated and complex. Something can be complicated but not complex by its function. So that's quite important to get understand. Not severe interdependencies between components. We have been discussing this on the previous slide. Lots of dynamic paths. So even though there is an electronic circuit, there is no clear, it's perfectly designed and it's usually doing its function, and you can't expect much of dynamic, no, a lot of interdependencies between its component. Probably there is a motor, there are several valves, and all those things will be there, but it's not quite serious, so not quite severe in terms of other systems available in the nature. So basically, this is a kind of a human-made thing, and we have the predictable circuits there, limited number of components with the interdependencies. It's not severe interdependencies, but we know the circuitry, and it's very much well tested, and it's done by us. But in terms of the cat, it's quite unpredictable, mostly because let's say your cat, house cat is at one place at 10 a.m. We don't know at 10 to 20 where will be it sitting on, because it may be on the neighbor's house somewhere else, and there is no prediction there by its operation, because it's not similar to washing machine. You can't expect this outcome after 20 minutes, and which is you can predict quite accurately, but you can't predict accurately in terms of the location of the cat, your cat, after 20 minutes. It's a kind of, that's one of the complexities in comparing washing machine with the cat. And cat is definitely a complex system, because we have no idea, 100% idea. Even the vets have no idea of 100% of cat's circuitry of the cat, because it's a product of nature and evolved millions of years. We have a limited understanding by the biologist maybe, but it's not perfect, because this is not something created by humans, or it's not a product within a limited time developed by us. It's millions of years evolution by the nature, and we have no 100% understanding of the internal circuitry or body chemistry of a cat. It's definitely a complex system. And interdependencies, even we don't know the components, how the 100% components working together, including its brain, heart, and all those functions have a close relationship with each other, heavy interdependency. And so this is definitely a cat is a complex system, and the washing machine is a simple system based on these aspects. So similarly, I defined computer networks are complex because became complex with the interaction of interdependencies between multiple components are there in the network. We know that there are a bunch of cables, switches, routers, and there can be multiples of them. And there are control plane protocols, data plane, and all those several aspects are there, and it's increasing or each and every day and evolving. And it's something like it is difficult to understand by a single person or collective the small, because it's number of interactions between the components are developed over many decades, and it's very difficult to get understanding of a large network system and its functionality. So when you are troubleshooting and designing the networks, you need to get your view of understanding that network is not a simple thing and it's a complex systems. Somewhat similar, equivalent to CAT, not similar to the washing machine, which is a single entity. The network is the entity with a multiple components with the heavy interdependencies between all the components. So that's why we need to have fundamentals built on it and rule of thumbs built on it, and a lot of research has gone through to build the best networks or resilient networks. So if you have the perspective of complexity on the network design and the network troubleshooting, then you are quite safe in terms of running your network or enabling higher uptimes. Okay, let's go into the few of more details in terms of the networks as complex systems. Okay, the previously we have been discussing the robustness. So in this particular diagram, complexity in highly organized systems arises primarily from design strategies intended to create robustness to uncertainty. When you are designing the network, you need to build the robustness, address the robustness to uncertainty, because there can be issues which you haven't expected when you are designing. So you should expect some of the known things, and unknown issues may arise, can be considered at the design stage, and even in the troubleshooting stage. If you are monitoring troubleshooting, if you see certain anomalies, you can analyze further in terms of predicting the future. There may be serious issues in future based on these outcomes. So the messages you are getting or the predictions you are having. So basically what this diagram says, or this graph showing that when you try to increase the robustness with the various components, let's say you are adding number of devices, you initially add a couple of devices as for the redundancy to improve the solution. Then you thought of adding another device, third device, for the further redundancy. In this case, it's not always enabling the increasing the complexity. Let's say you initially had a couple of switches to make it redundant. If one switch fail, other switch will take over the switching functionality. But if you decided to add third switch to reduce the downtime, with expecting if two switches fail, you have another one. In terms of perspective of robustness. But that's your intention, but outcome can be different, because when you are increasing the number of devices, when all the three devices are up and running, there may be failure scenarios with increasing the complexity. So when you are increasing the number of network devices or redundant methods, then it's not, maybe your intention is fair, but in the perspective of robustness, but your increase of complexity of the network, again making more issues. Rather, even it doesn't end the solving the issue you initially understand, but it introducing new issues. Then that making increase the complexity and the effectiveness of the solution. For an example, the same example, if you added another switch, third switch for your robustness, now you need to interconnect all three switches by using a mesh kind of a network. and your number of network links will be increased, or the link failure count can be increased due to increment of the links. And there can be suboptimal scenarios when on the partial failures. If you have number of components, it's increasing the failure counts as well as the complexity. This is the idea behind that. You need to, when you are designing or having a network or giving a recommendation on the robustness, you need to think in terms of the shoes of complexity as well. So minimize the target will be increase the robustness, but minimize the complexity as well. So where this diagram shows, when you are increasing the robustness, trying to increase the robustness, it will definitely increase the complexity. So then the solution effectiveness may not improve as expected, because it's introducing more issues in terms of your introduction of new components or the additional components. Any question on until this point? So let's discuss on the there is somebody from the fiber networking, so from Sri Lanka Telecom, I guess. So this is an unstructured network. The previous few decades back, initially people started server farms or the data centers, and they start the demand increased, and network administrators usually adding more and more devices, adding more and more components in the network data centers or the server rooms. It became something like this. So if you build or scale the network without structuring it, so you get you can get unstructured network without considering the scaling factors. You can end up with something like this. So it is quite difficult to manage, quite difficult to troubleshoot. The documentation is somewhat difficult, and identify the failure points is difficult. So if there is a failure or the failure in terms of application, the troubleshooting take long time. So unstructured network make a lot of issues in terms of if you haven't planned it from the design phase with the life cycle approach. So it will make a mess in terms of your organizations, and it's even if you change the staff without structuring your network, then even if you have the best network ops team, it's if it is not structured well, it is difficult to troubleshoot, and you can't predict the uptime of the year per year, and all those things will happen. And I just wanted to highlight few of the false analogies within the industry among certain few people. So it's a common saying that if it works, don't touch it. This is kind of a false analogy, which is encouraging the unstructured networking behavior. For an example, this is one of the oldest switches or network device from D-Link, and it's connected for a small business in the manufacturing area, I guess. Still working for more than 10 years, I guess. So if it is working, don't touch it. Can be catastrophic, because if something goes wrong, if you don't have a backup, so you need to wait few weeks or months to get new equipment, and you haven't planned for a work around, and your entire company or entire network the applications or network operation may be interrupted with single point of failure. And if you don't have a backup plan, your business will be hold for another week or two until you get your network devices, enterprise network device order finalized and purchase order, and then you need to import some of these devices because these are not they may not be available in local depot, and you need to wait for few weeks And if there is something in these periods like transport is a question between some of the countries and it take more lead time, and you are in a risk because you haven't assessed the risk, but you are just believing the scenario that if something works fine and how dusty, if it is, you don't no need to worry. This is a kind of a false analogy. You need to redesign this network with enabling the redundancy or backup devices having, and you need to maintain this control plane output from the operating system of the network device, showing that its uptime is 10 years and 15 weeks. These are some of not the same device. I think you need to restart your devices. You need to take care of your life cycle approaches. And this is not something you need to follow in terms of your IT management, systems management, network management. You need to have life cycle approach without following these false analogies famous among some of the peoples, because modern day infrastructure, network infrastructure and the IT infrastructure is heavily reliant with the application, not like we are mostly the paperless office these days, and the applications are almost automated with the software. And so it's quite important to not to consider on these false analogies. So that's something I wanted to highlight, and before going into the different planes. Any questions until this point? Okay, let's move ahead in terms of the different planes, 3 different planes. So there will be questions in terms of final examinations usually, and it will be heavily tested on your assignments as well. So control plane, data plane, and there can be another plane which is called management plane. In this particular network device, this is a switch. You have 2 different planes. These are quite logical, but to understand the switch, the previously I mentioned you that switches, I wanted you to get understanding of the definition of network as a virtual space rather than thinking that it as a hardware network devices. So in this case, we are thinking getting the logical model of a switch, not very much focus in terms of what are what are the silicon it has built and what are the circuitry. It's a different question or different perspective. For the most of the modern day network troubleshooting, we are troubleshooting in terms of the aspect of dividing the network devices by its planes. In this case, which we have 2 logical construct logical separations, which is as a control plane and data plane for a switch. So data plane addressing doing the forwarding of packets. It's usually the forwarding from one port to another port. There can be incoming ports. There can be a force which can have incoming and outgoing ports, and some of the ports are a full duplex. Incoming and outgoing can be done simultaneously. And in this case, port 1 sending a packet and need to forward it to port number 2, and its forwarding function handle usually the swapping or the packet from port 1 to port 2 will be handled by the data plane of the switch. There is another plane which is controlling the forwarding, because you just forward the packet. Usually, if you have a hub without a control plane, without a management plane, then you have data plane only. Traditionally, the initial network devices like hubs, they don't have a management plane, they don't have a control plane, they just forward traffic from one port to other ports. For an example, if you send traffic from the machine 1 to the port 1 of the hub, what it does is it's getting the message from the port 1, it's flooding to all other ports except the one it received. And intended receiver must identify it is addressed to him based on the MAC address and keep it. Others has to drop. So that's the function of a hub. It doesn't have a control plane, just a data plane. But this switches having something called control plane. It has something called MAC address table. It's filtering the traffic. It doesn't get the input that get the traffic and flood to all other ports. It's just forwarding it to the intended port, which is having the correct MAC address. So you can others can communicate simultaneously without flooding all the machines connected to the hub. So switch does it by using some different plane other than data plane, which is called control plane. Control plane having for the switches having MAC address table built-in. So the MAC learning process and the filtering of ports handled by this control plane functions. So it's usually there is another protocol. I think you have been learning this on the previous semesters on these protocols and standards in another course. There's something called address resolution protocol. We can discuss on a later topic as well. This address resolution protocol is an IP address to MAC address mapping function handles on the host. So address resolution protocol is another smart control plane protocol, which is quite useful on the filtering of traffic, and it's we can discuss details of the ARP when we are discussing the TCP/IP stack and troubleshooting. So basically routing protocols. If it is a layer 3 switch, then you can run dynamic routing protocols, not only the layer 2 functions such as MAC address filtering. So all these three functions, address resolution protocol, which is mapping the IP address to MAC addresses, and the routing protocols, which is routing the protocols between different subnets, the MAC address table, which is to avoid the flooding like hubs. And all three control plane protocols can be run by this using control plane of the switch. It has its own switch processor to handle these control plane functions. It's not a dumb device like hub. So store and again it has the enough memories to store information on the dynamic forwarding tables like MAC address table or the routing tables, and the forwarding decisions taken at the control plane based on the rules given to it or the protocols implemented there. So it can be implemented with the security in perspective or the business continuity in perspective or the controlling the traffic, controlling rules like access control list, and all those things can be implemented with the on this control plane layer. So that is the importance of having the additional control plane, just rather than just having data plane in the network devices. This is just an example. Any questions until this point? Okay, now if you purchase the network device like something similar to switch in this example, you are getting both control plane and data plane on this particular device. So each and every device has its own data plane and its own control plane, which is a kind of situation we call distributed planes, which means each and every device having its own data plane and control plane on its own device. So when you are configuring the device as a network configurator or network implementation engineer or the configuration engineer or the troubleshooting engineer, you need to connect each and every individual network device by using your laptop and connecting it to a console pane or the management port, console port or the management port, and configure each and every device individually. Sometimes you can SSH to the management port and configure it, or sometimes you can connect your network laptop device by using a console cable, and command line console cable can be console commands can be pushed by the console software or the command management plane implemented there, and then configure according. So each and every network device has to manage and configure separately. So there is so this is a quite tedious process when the network is scaling, because if you have limited number of devices within your organization, this is fine, because you just have to configure each and every device, so you don't need to worry on the central configurations. But when networks are getting scaled, and you need to with the thousands of network devices, and we have large ultra large networks like cloud networks, and those required to wanted to separate this control plane and data plane, and for the scalability of the configuration and management. So it is difficult to manage distributed planes if you have thousands or the thousands of network devices on your network, because you need to manage each and every device separately, because each device has its own control plane. Now, once you the idea of separation of control plane from the forwarding or the data plane came with the scalability requirements. So now it's a kind of this is the design or the idea evolved with the requirement. So it is basically this idea emerged from initiated from Stanford University. They developed a central controller with a protocol named OpenFlow. So now you can have a central controller and connect all the switches with the central controller, and push your configurations or control your devices by using this central controller. Central controller and the network devices are intercommunicating for the control functions by using something called OpenFlow protocol. This OpenFlow protocol developed by Stanford University. So it's a kind of open source protocol, or the famous among open source community. So this is the function when you have a large network with the thousands or 10,000s of devices or millions of devices, then you can control from the central location, and you don't have to visit each and every device, and you can push from one location, one central location, to all the other end network devices with the configuration requirements. Okay, this is the idea on the centralized controller with the separation of planes, which means end network devices just having forwarding plane. The control plane is centralized at the controller, central controller. So between them, the communication is done by a different protocol, which is named OpenFlow. This was the idea of and the requirement to separation of control plane or different plane, and implement the centralized control for that based on the scalability business requirements. But it doesn't end from there. After implementing this, people got an understanding. Now we can further improve. For an example, you can see there are 3 layers in this software-defined networking. There is something called software-defined networking, emerge with the idea of centralized controlling and the separation of planes. Now, architects have built a model which applications then directly access the centralized controller and doing pushing its own configuration, because now you are giving power to the it's possible to give centralized controller to your developers as well, application developers. Now directly applications can use the network as a big business function, because network is previously just supporting the applications. Now the network can become the business application itself. With implementation support to the integrated into the network layers. So in this case, for an example, let's consider the bottom layers. Infrastructure layer just having network devices, and control layer, you have the central controller. You can push configurations dynamically. For an example, let's say AWS, Amazon Web Services, they have ample amount of the large amount of network devices. They need to change workloads from the one place to another place dynamically, and there will be thousands of network configuration changes per day per device. So it is quite difficult to handle by humans, because there are human errors and humans have limited capacity and all those things. But by using a central controller, you can change quite fast, as many times as possible within a day. Of your network configuration changes are possible. So that's the idea behind it. So control layer can push any configurations quite fast and change the configuration fast by using the same method, using open flow protocol in this diagram, connected with the control layer to the infrastructure layer having the hardware network devices, and the connected to management flow port, and open flow pushes configuration by the centralized controller deployed on the control layer. And this software-defined networking emerged with providing access to the application layer for the controller. Controller can be accessed from the application layer. For an example, you can write applications to have the access to this by using APIs to the controller layer. So then, based on the application demands, you can reconfigure the network by pushing the requirements by using APIs, and reconfigure the infrastructure layer based on the application requirements automatically, or you can program it, or developers can give the access for the developers. So this is the idea behind software-defined networking and separation of the different layers. And this is the architecture built over the recently, or within the last decade, with implementing the idea of software-defined networking. So now you have understanding of, in terms of troubleshooting, you need to have the perspective of data plane, control plane, and the management plane for the configurations, and the separation of control plane with the data plane, and implementing the centralized controller by using protocols like OpenFlow. And then this software-defined networking architecture, which is benefited by isolating the control layer from the forwarding layer, and have providing application access to the control layer for your business applications to handle the network dynamically. Any questions until this point?
No, sir.
Okay, somebody has question? Yes, Apura.
No questions, sir.
All right. Okay. So this is quite important in terms of modern networking. For the traditional networking, you can depend on this going each and every network device and connecting with the console and configuring all those still people do with the CLIs, but now nowadays mostly this controller functions and uh, even the vendors are more moving forward this direction, which encouraging clients to move to centralized controlling with rather than depending on the old traditional architecture of maintaining the network devices. And there is another concept which we are usually, this is emerging with the software-defined networking, but it's not directly related. We have been discussing this, one of the slides we had this, right? Let me go back to. Okay, let me check. Okay, this is the slide again. We are coming back to network engineering works in largely virtual space, although there are wires and devices. I previously mentioned that the hardware device, there will be hardware devices, but mainly we are more concerned in terms of troubleshooting aspects or fundamentals. We need to see the network as a something within the virtual space. Now with this cloud and virtualization like VMware stuff, you can see that there is an evolution with the virtual function network function virtualization, which is virtualizing the network devices. Now you can see that within a cloud you don't need to purchase separate router for that. Previously, each and every network component has its own hardware, and or the appliance implement with the hardware appliance, you can implement router, switch, or any other function with the network requirements. Those you need to purchase and wait from the vendor and wait for few months to be few weeks or months to be delivered on your site. And then you need to configure, and it take lead time is quite high and you need to deploy. But for the cloud and other environments, now the same vendors almost providing virtual network devices. For an example, let's say Cisco has their own hardware switches, and now with this VMware deployment, they can provide their own virtual switch for the VM environments. Similarly, for the cloud, you can get virtual routers implemented. You don't need to have hardware separately purchased with the appliance to have firewall anymore. You can have your virtual firewalls implemented on the VM instances. So that's called network function virtualization, which leading mostly in the industry, because if you need to have firewall functionally implemented on your VM network, you just need to deploy the firewall instance with the VM. So for the functionality, it's a kind of the easy approach, a fast approach, which you need to implement the firewall or the network function by virtualizing the functionality. That's called the network function virtualization evolution. So now this is the idea. It made us to build the network quickly and deploy it fast without taking longer time. Still, there are hardware devices, because there are sometimes when you need to optimize the performance for low latency and certain workloads. And in those cases, we depend on hardware devices. And now hardware programmability is also possible with the field programmable gateway array, FPGA controllers, which is somewhat different kind of programming. which you require to have in terms of possibility of deploying hardware devices with the custom programmability. So it's provided. But in this evolution of virtualizing the network functionality, network functional virtualization is quite important in terms of scalability in the clouds and as well as the building virtual environments. So this made complete the network as a virtual construct. So you don't need to have hardware devices anymore to have network functions. You can implement those network functions on the VM virtual environments as well. Okay. Let's start on so today we covered on network complexity aspect, targeting the troubleshooting and the structured and unstructured network, false analogies against the life cycle, and control plane, data plane, and the management plane, and separation of the planes, and the centralized controller, and the software-defined networking architecture perspective, and the virtual network network function virtualization. So let's go back to the network failures and the understanding the uptime and the failure predictions. So previously I explained you how to calculate the uptime as a percentage per year. This is an example diagram calculated for different percentages. Usually, we expect network to run most of the time. In this case, started the availability with the 90% availability. So at least in a modern day networks, we expect 90% uptime on the business hours to run the applications. Even those are not critical, we still need to have emails and probably day-to-day business functions to be run, like accessing the file servers and all those things, printers. You need to have, if your network is available only 90% of time, may be sufficient, because if it is not mission critical. But if, let's say, let's further understand the 90%. So let's say you have 30 days per month, and 90% is usually divided 10 and 30 days 3 into 9, 27. So 3 days can be down and 27 days can be up. So it's 3 days downtime can be distributed among. I think it's still there may be concerns among the users, application users, because if you try to send a printout from your laptop and some days it's not working for few hours, then it's difficult to get the printout from the Wi-Fi or the network printer. So it's a concern. It's impacting the business. And if you send an email to the email server, sometimes there may be issues in terms of sending emails. If there is an email which required to send within 30 minutes and your server network is down for 30 minutes, and there can be issues. So it's quite important to have more availability, high availability in the modern day business functions, because you're not working on the physical work processes anymore. The most of the offices are paperless office. You're not working on the purpose other than the traditional government institutions. Mostly the modern the private institutions as well as the government institutions. For an example, even the Colombo University is a government institution. We are having these sessions the masters of this sessions through by using virtualization or the Zoom application. We need to have more than 90% availability. If it is down for 1 hour, 3 days per month, and maybe we can't have 15 sessions on the same time, same time frame of the day. So it is quite difficult to run, even though 90%, but it may be acceptable on some environments. So usually we expect more than highest availability on some of the applications. For an example, let's say stock markets, stock exchanges, or the banks, they expect higher availability based on this the minimum downtimes. For an example, let's say your bank, there can be a bank with a requirement of 99.99, which is 4 nines in terms of the layman terms. They have application requirement to run their banking application with the 4 nines, with the least downtime. The expectation is downtime per year is 52.6 minutes for entire year. And downtime per month, this is based on the business hours. Downtime, nowadays banks should work for 24 hours based on the online banking. So downtime per month, 4.32 minutes. Downtime per week, it's roughly around 1 minute. So when you are defining these availability percentages, you need to consider these downtimes and design your network based on the application availability percentage requirements. Because when you are selecting the device to build your network, you need to address from there onwards. Not only selecting the devices with highest availability, but you need to build the architecture based on these numbers. And not only that, you need to monitor the network, manage the network. When there are issues, you need to have backups of network devices. So this sign the SLAs, service level agreements with the vendors you are working on. You need to define based on these numbers, availability numbers. So you need to replace fast. You need to build the architecture with automatic redundancy and reduce the complexity as we discussed to avoid unintended consequences. So based on your availability number, you can start the designing process and plan the troubleshooting and monitoring processes as well. So this is quite important to understand. The availability number calculation when you are designing and handling the support infrastructure and the planning for the troubleshooting phases. So you need to work on this as a starting point. Let's move to the network failure aspect. So network outage is the loss of network resources, including routers, switches, transport facilities because of following. So there can be outage of your network for the applications. It can be a complete failure. None of the applications can be run due to hardware or software component failures. If you haven't designed redundancy or the resiliency on your network, then it can be a complete failure on a single point of hardware or software component failure. If you enable redundancy, it's very rare. And there can be partial failures. For an example, some of the applications or some of the traffics pass through, but some parts of the network or some of the applications are not functioning as expected. So that's it. Basically, network outage is a complete or partial failure. It may not entire complete failure. It can be a partial failure as well by the definition. And there can be a power outage. So this is not directly related to the network devices or component, but the power source can be, if you haven't planned redundant power, UPS power, then it is impacting. It is again considered as network, even though it's not network device or component failure. The power failures usually considered as network failures because it's automatically fail the network to function. It's dependent on function power. Scheduled maintenance such as software. Usually we are getting from the institutions, we have a downtime on the weekend from this time to this time. And usually scheduled downtimes also considered as failures because you are reducing the availability or increasing the downtime. You cannot use the network. And operational errors such as configuration. These are the scheduled maintenance. You are quite, you know in advance that you need to use this downtime for the maintenance. It is pre-planned. But there can be situations of, such as operational errors which make your network down with the configuration errors. There can be human errors you have configured improperly and making it down at some point. So operational errors can be there, which is quite unintended, and surprises will be there. And finally, the acts of nature such as floods, natural disasters can impact data centers. So that is considered as network system failure. You can build your resiliency around that, having disaster recovery sites and the cloud-based deployments and something like that. Backup strategies can be, redundant strategies can be planned accordingly. So network outages usually defined within these terms. And each network outage can be broadly categorized as either unplanned or planned. Can be scheduled, planned one, or it can be unplanned one, as because there can be several ways of networks getting down. And fault tolerance of network hardware and software component is crucial to deliver user services with negotiated service level agreement. As I mentioned, the partial failures are also important to consider. Even though your application is running, it is running very slow and it is difficult to tolerate. So you need to define the service level agreement, especially when you're getting an internet connection or wide area network connection. You need to consider service level agreements based on the tolerance of operation. And it is apparent that reliability and stability of the network hardware and software are absolutely crucial for building reliable and available networks. So you need to consider when you are purchasing hardware or software before you purchased, about the reliability and the ratings, as well as commitment from the vendors. All those things need to be considered based on your criticality of workloads and the applications. So that is about the definition of network failures and the categorization of it. Then we can categorize again the failures to based on the components. There can be hardware components in your network and the software components in your network. Just give me another 5 minutes so we can finish this off on 10:35 and then go for the break from there onwards. Network hardware failures, based on experience, you will find that most of network problems are hardware related traditionally, because most of them are the cable failures based on the statistics. Nowadays, these statistics are quite different because we are mainly dependent on cloud and virtualization stuff. And the previously traditional networks, mostly based on the surveys, there are cable disconnections and hardware disconnections. So these stats are different now, but on-prem mostly still on the cable stuff or the hardware components. One of the most effective techniques for reducing unplanned hardware-related downtime in a network is the use of redundant hardware. That's why we are having multiple switches. Initially, I shown you the enterprise campus network, which is having a couple of core switches, couple of distribution layer switches, access layer switches, and you need to consider where I should put 2 devices, or do I need to have put more than 2 devices? In terms of enabling redundancy to address the hardware failure is the best approach in terms of network design and avoiding the failures, including line cards, not just having couple of network devices. You need to consider having line cards, link redundancy, and the other aspect as well, power supplies, the fan modules. All the hardware components need to have redundancy, not only just having couple of devices, but need to address the partial failures, components of within the devices as well. So for an example, when you are selecting a network device, you need to consider the redundant power modules, redundant fans, and additional ports if you are configuring the multiple link redundancies by using the same switch. Different additional line cards for the chassis-based routers. So you need to address single point of failure when you are planning around the hardware failures. The famous rule of thumbs to avoid failures defined here: no single hardware fault should be result a loss or degradation of user traffic. This is to avoid single point of failures. System downtime should be less than X minutes per year. You need to purchase and plan for device downtime based on your availability number given at the planning stage by the business stakeholders. Then the line card, switching fabrics, and the redundant subcomponent need to be planned for each and every device. The control plane hardware module should not be single point of failure, because we discussed the control plane and data plane. You need to consider on the control plane redundancy as well. If you need multiple supervised engines for the chassis-based switches, which you need to be if one supervisor module failed or control plane module failed, it should automatically move to another supervisor module. So you need to have not redundant modules there as well, considering the control plane, not only addressing the data plane in terms of planning the hardware failure and the redundancy around it. Network devices should be capable of service recovery from link node. You just need to you can't just depend on device failures. There can be link failures. So you need to plan for the link redundancy as well. Connecting multiple switches and multiple links from the host devices, and the multiple network interfaces or network cards can be put from the server side. So link redundancy you need to address in terms of avoiding hardware failures. So device redundancy and link redundancy are quite important. This is how this is some of the best practices or rule of thumbs to handle hardware failures. And then go to the network software failures. So redundancy is the best approach in terms of addressing hardware failures. But let's find out what about the network software failures. Network software failures mainly based on control plane of the network devices, which is we discuss the control plane separately. Designing of network for high availability requires designers to consider the reliability of each network software component as well. So if you have a 4.9 requirement, then the designers need to consider the reliability of the software components as well. For an example, we discussed on the network function virtualization. If you are putting a software firewall or software device, you need to consider the reliability of software based on the ratings and the industry information, and you need to careful on selecting the software with the reliability factors. High availability in network software infrastructure enables seamlessly recover from most failure scenarios. If control plane such as supervisor switch over to process, as initially the previous slide I mentioned that supervisor is running the control plane with the software, and supervisor failover should be addressed in terms of high availability environment. If you are using chassis-based switches, you have bunch of line cards for the network switches for the connectivity, but control plane runs on the separate modules which call supervisor. Those are having processors included that, and if one supervisor fail, other will take over the functionality with the redundant supervisor. And sometimes active or active backup scenarios are there with the supervisor selection. You need to address the redundancy, even the software running, control plane software running as well. And even there may be requirement to restart sometimes. So you need to have another supervisor module to network to be functions as usual. But when you're restarting the supervisor module, still you can forward the traffic, but configuration changes sometimes not possible. Some of the things are not possible when control planes get down. So you need to consider control planes specifically on these software failures. Finally, the network designers also need to consider protocol attributes such as complexity. We discussed the complexity, and the software complexity and the implementation complexity has to manage and maintain based on the convergence of multiple network devices, dynamic routing protocols, dynamic protocols with running between different devices, and the overhead of those control plane functions. You need to have enough processing power to function, do the control plane functions. So you need to measure the usage of your control plane devices or the software components as well. So those are the so these are the reference book in related to the first third session. So I included network complexity 2 books, and this previously I explained the black zone, which is from the risk management expert, and the making things work is from the complex systems expert, and another one is navigating network complexity, and other 3 have been using for the troubleshooting and the network design, the design patterns as well. So these are useful in terms of if we want to have deeper understanding of the topics we discussed in this section. So let's take a break. Probably we can meet up again after 15 minutes. I will put a clock on this. Okay, thank you very much. Let's meet after 15 minutes for the session 4. If you have any questions, you may ask now, or we can ask after the session break as well. Okay, let's meet after the 15 minutes then.